Morning, everyone. How's everybody doing? Is anybody having issues logging into my courses? I can't seem to log in this morning. Yishan has a question. Find DU. I'm going to assume it's DUDT or DUDS. Or this might be referring to something we did not do. Right, yeah, exactly. So this is known as a differential. We did not cover it, but let me tell you what the answer is. du is du ds times ds plus du dt. Okay, thank you, Yishan. Yeah, so differentials, it's like a total derivative, if you will. We did not cover that. Nothing important as far as this course is concerned. Quinn is asking if we're going to see Jacobians. Indeed, we are. We're going to see that momentarily. Carl is having trouble opening it as well. Yeah. Yeah, and so is Samuel. I've been having this issue for many weeks. I emailed IT. They're very slow in doing anything, and they keep offering stupid suggestions, like I'm not using the right address and stuff like that. So. Emily, let me give you the TA's email in case I forget. Vivian is saying that she doesn't see WebWork 2. That's correct. WebWork 2 is going to be on curves. We'll see how far we get by Thursday. If we have done enough, I'll open up WebWork 2. If we have not done enough, there will be no WebWork 2. I don't know how many questions it is. Questions on polar coordinates? We'll do a few more examples. I believe WebWork 4 is due on Sunday. Is that right? I think it's due Sunday. I mean, I originally had it due on Monday, and we can postpone that to Monday. It's not a big deal. Monday is our last day of class, so you want to. Well, I mean, that's the thing, right? I mean, if I open up a WebWork 2, I got to leave myself a few days. As Ahmad points out, we don't want the same due date for 2 assignments, so I'm giving myself a bit of wiggle room there. All right, let's move on. Bryn is asking if we're going to introduce new material on Monday. For sure we are, yes. All right, consider this example. Find the area enclosed by one loop of r equals 2 sine 5 theta. So take a moment and graph this function in the, well, I say function, but it's not a function, right? Graph this curve in the xy plane. Of course, in the r theta plane, this is just one, two, three, four, five, right? This is the sine graph, but it goes 5 times faster, right? The period is 2 pi over 5. And the amplitude is 2. But that's in the r theta, or theta r plane. What we want to graph it in is the xy plane. So you know what's you understand how to translate one from the other, right? Here, r is the distance from the origin. So if it's 5 times faster, 2 pi over 5, this is 4 pi over 5, 6 pi over 5, 8 pi over 5, and 10 pi over 5, which is 2 pi. Ahmad is asking for tips on how to not lose partial marks. Show all your work. I've been getting, yesterday I released the midterms because people wanted to see how the marks they got on each question. I thought you could do that directly on CrowdMark, but apparently not. So I released the midterm so you could see exactly what happened, how many marks you got. Look, people have been using Wolfram Alpha or online software. I said that was fine. There's no issue there, but there's a trap, right? If you are relying on the software to do the question for you, then it shows in your work. And we don't want that. In the instructions at the beginning of the exam, it says that online computational software is not justification for your work. Keep that in mind. In particular, when I ask you to approximate something to within 3 decimal places, if you enter that on Wolfram Alpha and it gives you 0.946, well, that's not justification. And it says in the instructions that I will not accept that as any justification. Yining is asking how to find, back to Ahmad's question before we move on. Again, the idea, show all your work. The whole question has to be self-contained there. And imagine another student picking up your proposed work. There has to be no hesitation. That student has to understand exactly what you've done. And the work has to be yours. So that's it. Show all work. Make sure all work is yours. Justify every step. And that's it. All right. Yining is asking how to find the boundary of an integral under polar coordinates. Well, that's the thing. That's why graphing is so important. You have to graph first to understand what's happening. We're going to do a few more, so you'll see what happens here. In particular, let's graph r equals 2 sine phi theta. In fact, for the question, we don't need to graph all of it. But for practice, we're going to do that just to understand what is happening and how this graph comes about. So you've had some time, perhaps you've graphed it already. Sine starts off at 0. So r, which is the distance from the origin, r starts off at 0. So you're at the origin. And then you're increasing all the way to 1 and back down to 0 at pi over 5. So increasing all the way to 2, I should say, and then back down to 0 at pi over 5. And then from pi over 5 to 2 pi over 5, which is somewhere in here, your function is negative. R is negative. So instead of graphing it here, I'm going to graph it in the opposite direction right here. It does not cross the y-axis here. This is a slight issue there. And then from 2 pi over 5 to 3 pi over 5, same thing. But in a positive direction. And from 3 pi over 5 to 4 pi over 5, which is somewhere here, it's negative. So, and then 4 pi over 5 to 5 pi over 5. 5 pi over 5, which is just pi, is going to be positive. And then 5 pi over 5 to 6 pi over 5 is negative. So instead of graphing it here, it moves back on itself right here. And then same thing happens over and over again, right? So that's how this is drawn. For this question, we didn't need to draw all of it. It was just asking for the area enclosed by one loop or one petal. So there it is. One petal is realized in 0 to pi over 5. So the area of one loop, 0 to pi over 5, 1/2 your function squared d theta. Expand. You know how to integrate. Sine of 2 pi is 0, sine of 0 is 0, so this is just pi over 5. Yining is asking, is the area under the x-axis negative? It's a valid question. First of all, area is always positive. So if that's the question, area is always positive. You know that if you're integrating a function underneath the x-axis, then it's negative of the area. But that doesn't occur here, right? Because remember how the area is calculated, right? It's like a wedge. It's like a part of a circle. So this is going to be positive, or this is still going to be positive, right? Because it's a part of a circle. But it's asking, instead of graphing, to find the limits, can we solve 2 sine 5 theta equal to 0? Well, what? I mean, here you're making the assumption that the petals are actually emanating from the origin. What if they were not? Right? What if this was actually offset? So it's dangerous to just try to solve something without graphing it. Yishen is asking about odd and even properties here. Not in this case, but the idea still applies. The idea always applies when it comes to integration. Right? But here, our limits were not from negative a to a, so there was nothing we could do about that. Consider this. We're looking for the area inside this business and outside of that one. Let's graph this to understand what this even means. So let's look at the sine graph first. And let's use this to translate into a graph on the xy plane. So sine starts at 0 and goes all the way to 1 at pi over 2. So this starts at 1 and goes all the way to 0 at pi over 2. And then this goes from 1 to 0 at pi, so this goes from 0 back to 1 at pi. And then sine becomes negative, so this grows all the way to 2 at 3 pi over 2. So this is going to grow, the distance is going to grow all the way to 2 at 3 pi over 2, and then goes back to 0, so this goes back to 1 at 2 pi. And of course, sine being periodic of period 2 pi, this is just going to repeat. So you get this cardioid business. Yishen is asking if we want to find the area of this thing from 0 to 2 pi, can we say it's the same as the area of one petal due to the odd property? If you did the integral from 0 to 2 pi, it would be actually the same as 10 petals. So it would be 10 times this. You could use that. All right, so there's your cardioid. R equals 1 minus sine theta, right? Kind of looks like a heart. All right. And then r equals 1. What is that? Right? It's the distance from the origin is always 1. So the distance from the origin is always 1, regardless of what theta is. That's the equation of a circle. Well, can you see it? All right. So what do we want? We want the area inside this, but outside the circle. So you see what area we want, right? We want this area right here. The area below the circle, exactly that amount. All right, so let's set it up. Well, this corresponded to pi. So this part of the cardioid here is from pi to 2 pi. So 1/2 of your function squared, that would give you the whole region below the x-axis, right? The whole thing in your cardioid. You don't want the whole thing, you want to subtract this, right? So this gives us this whole thing right here. That's what we have right now. We don't want this region. So let's remove it. You can remove it as an integral from pi to 2 pi as well of 1/2 r squared. But of course, you know what the answer is going to be, right? It's just half of the area of a circle. So 1/2 pi r squared, where r is 1. So this should be pi over 2, which is clearly is going to be. I'll leave you to integrate this. This is trivial. The important thing for us was the setup here. And there we have it. Let's do another one of these. Same question. Find the area inside this and outside that. Take a moment, graph these. Exactly that, Yishen, right? In general, the area is not going to be negative. So it's not going to cancel anything out because you're integrating something that's positive all the time. Absolutely. And this is guaranteed by the setup we did, right? It's these wedges which always have positive area. So regardless of whether your function is underneath the x-axis or above, what we're measuring is the area. Always the area here. Notice it's not the integral of your function. It's 1/2 function squared. Let's just quickly draw the graph of cosine. In the theta r plane. So that we're able to graph these two functions in the xy plane. Cosine starts at 1, so r is going to, if I'm looking at the first one, r is going to start at 2. It's going to decrease, cosine decreases to 0, so r decreases to 1 at pi over 2. And then r keeps decreasing to -1 at pi, so r goes all the way to 0 at pi. And then just does the opposite. So again, you have this sort of cardioid here happening. And now let's draw the second one. Here, r cosine starts at 1, so r is going to be 2 minus 1. R starts at 1 and goes all. So first of all, what was this? This was 1 here. So r starts at 1. Cosine decreases to 0 at pi over 2. So r is going to increase to 2. It's a problem, but whatever. So r increases to 2, and cosine keeps going to -1, so r is actually getting larger all the way to 3 at pi. and then does the opposite. Something like this. So we're looking for the area inside the cardioid, but outside of this thing. So I think it's clear that this is what we're looking at. Right? And it becomes important to work out where these intersect. Right? That's going to determine your angle theta. And R is going to go from here to there. Right? So you're going to have these wedges here. Right? So it's going to be the volume of the big one minus volume of the small one to give you the stuff in between. So where do these intersect? Let's work that out. One cosine is 1/2, very nice, right? 1 plus cosine theta is equal to 2 minus cos theta, right? R is equal to R. And bring this over to the other side. 2 cos. So cosine is equal to 1/2. And you know that to be pi over 3. So this is pi over 3. And of course, cosine is even. So this is going to be negative pi over 3. So you could go from negative pi over 3 to pi over 3. Or there's obviously some symmetry happening here. So the area is going to be twice the integral from 0 to pi over 3 of 1/2 large function 1 plus cos theta squared minus small function Yining is asking why minus pi over 3? Well, I mean, from the picture, we were expecting 2 points of intersection, right? One here, one there. And of course, using properties of the integral, you want, in order to have something positive, you want the angles to be increasing. Some of you might have been tempted to say, 5 pi over 3 to pi over 3, that would have given you a negative answer. Exactly that, Lynn. Exactly that. Well, I mean, you want to stay away from taking absolute values as we addressed that issue in Cal 2, because sometimes, I mean, it's a quick fix, but sometimes the issue is more important, and then taking the absolute value does not fix anything. So be careful, set it up properly, and there's no need to take absolute value of anything. This is the proper setup. I'll let you integrate this again. For us here, at this moment in time, it's the setup that's important. You know exactly how to integrate these things. So let's not waste any time doing that. All right. Maybe one more example. Do we? No, let's not. Let's move on. Let's move on to asking the question, just for fun, what about arc length? Can we calculate the length of these curves here? In the same way we did in Cal 2. Right? And let's recall how we did that in Cal 2. Right? First of all, what is happening in Cal 2, if you had a curve, we did a Riemann sum by looking at these straight lines, right? We did an approximation where these straight lines were really the hypotenuse of these right angle triangles, where this was the change in x and this was the change in y. So this length here was the hypotenuse of a right angle triangle, and then you added all of these up and you got an approximation to the length of the curve. Right? And you know the trick, right? We either factored out a delta x or factored out a delta y to get a Riemann sum, right? Because as it stands right now, it's not a Riemann sum. We need a delta something, delta x or delta y. But here, what are we graphing? We're graphing r as some function of theta. So we don't want a delta x nor a delta y. We want a delta theta, because everything depends on theta. Well, there's no delta theta anywhere to be found, so let's introduce it. Multiply by 1. Delta theta over itself. You multiply by 1, you're not changing anything. And now bring this into the square root. This becomes delta x over delta theta squared plus delta y over delta theta squared with the delta theta outside. And now you have a Riemann sum. And as delta theta gets smaller and smaller, the sum becomes an integral. Square root of dx d theta plus dy d theta times d theta. But again, let's recall that this is what you're graphing. R equals f of theta, where x, which is r cos theta, and y, which is r sine theta, in this case is really f of theta cos and f of theta sine. So let's work out dx d theta. Well, it's a product, so product rule applies. So you get this, and dy d theta is f prime sine plus f of theta cos. So if you square these and add them together, what do you get? F prime squared, cos squared. This times 2. Plus this squared. Plus this squared. This times 2. And finally, this squared. Hopefully some stuff cancels. You can see already this and that will cancel out. Here you have f prime squared cos squared plus f prime squared sine squared. So that these two together give you f prime squared. And then you have f squared sine squared plus f squared cos squared. Factoring out an f squared, you get sine squared plus cos squared, which is again 1. So f squared. And there it is. There it is. So the arc length formula becomes the integral from a to b of the square root of f prime, or f is really your r, right? So it's r prime squared plus r squared d theta. Let's take an example for fun. Questions before we do that? Is it the same idea for surface area? It's a similar idea, not exactly the same. Not exactly the same for surface area, and we're not going to discuss surface area, and I'll tell you why. Surface area is exactly what you do in advanced calculus. It's almost the whole course. So there's really no point in discussing it now because you're going to discuss it in length in that course. But the idea is very closely related to the partial derivative in the sense that if you have this surface, remember in the partial derivative, we had these two vectors, right? The derivative in the direction of x and the derivative in the direction of y. And from there, we defined the tangent plane, the tangent, the plane which contains both of these. And so, yeah, so if I call this tx, meaning the derivative in the x direction, and I multiply by some small constant delta x, and then this here, the tangent in the y direction, let's call it ty delta y, to make it small, then you'll remember that the length of the cross product gives you the area of this parallelogram. And if you add all of these little parallelograms everywhere on your surface, it gives you an approximation to the surface area. And that's exactly the formula you get. So this, where you're adding over x and y, this is tx cross ty, delta x, delta y, and you're done. As delta x and delta y get smaller and smaller, this becomes the double integral, tx cross ty, dx dy. This is your surface area. Again, not for us at this point in time, but in advanced calculus, that's what you're going to be studying. And you're going to be doing calculus on these surfaces. So you're going to integrate on these surfaces. You're going to have some function hovering above in a fourth dimension, and you're going to ask the question, what is the volume, the four-dimensional hypervolume between the function and the surface? And you're also going to see vector fields acting on this surface, so a new object which has nice physical interpretations, like a gravitational field or a velocity field for fluid. Imagine fluid passing through the surface, and you're going to calculate different things. Ahmad is asking, what if you do this by rotation? Well, the thing is, this formula has an equivalent. The surface area of rotation is a special case of this formula. So that's a very nice observation. As you know, of course, not all surfaces can be viewed as surfaces of revolution. But yeah, Yining is asking, after Math 264, we learned most of the calculus. Well, I mean, Math 264 is the last calculus course. So that'll be it. And like I said, it has everything to do with this. Calculus on surfaces. Let's take an example. Just a quick example. Why don't we take a moment to graph this? Just for fun, right? I mean, it's a new curve. We haven't seen this before. What does the graph look like? When theta is 0, e to the 0 is 1, so you're starting at 1. And as you are increasing all the way to pi over 2, this is increasing all the way to e to the pi over 4, whatever that is. I mean, we know it's bigger than 1. There it is. But that's not the, I mean, lackluster, if you will, right? Nothing fancy is happening here. What I want to bring your attention to is, what if we went the other way? What happens then? This is 0. What if we start plugging in negatives? What if we go, what happens from 0 to negative pi over 2? At negative pi over 2, this is e to the negative pi over 4. So it's 1 over e to the pi over 4. So, you know, it's getting smaller. And if you continue to negative pi, e to the negative pi over 2 is smaller, and it's getting smaller and smaller. And you see what's happening, right? As theta goes to negative infinity, what is happening to this? As theta goes to negative infinity, the whole thing is going towards 0. So it's spinning over and over again, getting closer and closer to the origin forever. And if you continue this, as theta goes to infinity, this whole thing goes to infinity, so this keeps getting larger and larger and larger. I mean, maybe it has to do with the golden ratio, right? Absolutely, we did not introduce that, but there is this nice relationship between that and the golden ratio. Very nice. All right, but all we're interested in here is the length of this part. So let's work that out. Here is the formula we just derived. So what is that? Here, this is the integral from 0 to pi over 2. R is this. So r squared, e to the theta over 2 squared, plus the derivative, which is e to the theta over 2 times 1/2 squared d theta. Yining is asking, why can pi over 2 and negative 3 pi over 2 give two different values? Should they be the same point? No. There's no guarantee that they're the same point, right? Because it's what you're thinking of is the point pi over 2 and 1. So r theta is 1 and pi over 2. You're thinking to yourself that this is the same as 1 and minus 3 pi over 2. And you're right. You're right. But here you have a function. You don't have control over what r is. Right? And the r is not going to be the same. Even though these two things they give different values of r. So it's not the same point. Ben, you're suggesting that this becomes e to the theta plus 1/4 e to the theta, absolutely, which is just the square root of 5/4 e to the theta over 2. Right, if you factor out an e to the theta, and antiderivative of that is going to be a root 5/4 e to the theta over 2 from 0 to pi over 2. And this is e to the pi over 4 minus 1. Absolutely. How are we doing here? Questions? Questions about polar coordinates? Because now we're going to tie this into the double integral. Have I made a mistake, Yuni? Square root 5/2 here, correct. But then when you take the antiderivative, because of the 1/2 there, I think we're good. All right. Let's ask the question. Well, is there a question to ask? How did I get the 5? Factor out an e to the theta, you get a 1 plus 1/4, which is 5/4. Let's go back to Cal 2 again and tie everything up. How do you integrate this? Oh, yes, thank you. I've made a terrible mistake. It's just a root 5. Thank you. Thank you, Cecile. Just root 5. Root 5, thank you. So x equals, sorry, trig substitution, Tony, correct, Ahmad, but not secant, rather. X equals sine, so that dx is cos theta d theta. And now let's think ahead to a situation involving a double integral. Suppose you had this double integral and you decided perhaps a change of variables was in order, right? Here we let x be a function of a new variable? What if we did the same thing here? What if we let x and y be functions of two new variables? So a function of u and v and another function of u and v, right? In a similar fashion as what we had done here. The question arises naturally, what is dy dx in terms of du dv? That's the question. What is the x dy in terms of du dv? Right here, you just took the derivative and you were good to go. Here, what could you expect? You might expect dx du, dx dv, dy du, and dy dv to play a role. It's not clear that they all do, but perhaps some combination of them plays a role. Definition. Given x as a function of u and v, y as a function of u and v, we define the Jacobian. dxy by duv to be the determinant of dx du, dx dv, dy du, dy dv. This is a matrix, absolutely. It's the determinant of this 2 by 2 matrix. Theorem. Theorem if you make a transformation then which transforms a domain D in xy to a domain E in uv, the double integral over Ahmad is asking, that is du dx times dy dv minus this, right? You know the 2 by 2 determinant here, du dx dy dv minus dx dv dy dv. Absolutely. Absolutely, right? It's the determinant of this 2 by 2 matrix. So if you decide to make a transformation, right, a UV substitution, if you will, then F in terms of UV, let's say, let me not write anything here, and then this dy dx, so let me call this J as in Jacobian. We define the Jacobian J to be this. You have to throw in the Jacobian. Well, the absolute value of the Jacobian. Right? So we were saying we might have expected dx du, dx dv, dy du, dy dv to play a role, and they absolutely do. This is the role they play. Why is this a Jacobian? What does it mean? I'm not proving this, but let's discuss what is really going on here geometrically. Think about what's happening. You are making this UV substitution, right? So you're starting in the xy plane with some domain D, and you're making this substitution. So you're transforming this into a UV plane, right? U and V. And this domain is being transformed into something else. How am I going to draw something else? So you see what happens, right? You used to have some area, and now maybe you have a different area. How do we compensate? And you compensate through the Jacobian. What this is telling you is that here you used to have these small, right? Think of a Riemann sum argument. You had these small rectangles of length delta x and width delta y. These are being transformed into small rectangles du dv, but there's a difference. What's the difference? The difference is the Jacobian. You throw in the Jacobian, to compensate for the loss of area. So this Jacobian measures how much the area changes by. That's what the Jacobian does. Yining is asking if the area always stays in the same quadrant. Of course it does not. It does not. This is just a general picture of what's happening that geometrically describes what the Jacobian actually is. Well, let's take an example. And the obvious example is the polar coordinates. If we make a polar coordinate substitution, right here, x is a function of r and theta, y is a function of r and theta. What is the Jacobian? The Jacobian, dxy by dr theta, d to e is going to be an approximation, or their values are exactly the same. Well, what I'm saying is, the theorem is this. So as delta x and delta y get smaller and smaller, the approximation becomes, well, in fact, let's say this, the ratio dy dx over du dv. Is this approximately, and as delta x, delta y gets smaller and smaller, this becomes equal. Let's say that. Or better yet, this is the theorem. When you're making a change of variables, you have to throw in the absolute value of the Jacobian. What is this? dx dr, dx d theta, dy dr, dy d theta. Let's work it out. dx dr is cos. dx d theta is minus r sine. dy dr is sine. And dy d theta is r cos. This is r cos squared minus negative, so minus minus is plus, r sine squared. And if you factor out an r, you get sine squared plus cosine squared, which is 1. So the Jacobian is r. So if you make a change to polar coordinates, you have to throw in the absolute value of r. It is customary that we usually make sure r is positive so that you don't need to worry about the absolute value. But some of you at some point may want to disregard that. So you have to be careful. Ran is asking, does the Jacobian only work for double integrals? It does not. We're going to, after this, discuss the triple integral, and you'll see that it's exactly the same thing. Let's take an example from the book. Let me point out, we've taken some time to work out the Jacobian for the polar coordinate transformation. This happens often enough that you don't need to work it out ever again. You can just refer to the result we got. You know the Jacobian for the polar coordinate transformation is R. Even on an exam, absolutely. On an exam, you can say that we know the Jacobian for the polar coordinate transformation is R. There's no need to work it out. It is, of course, a nice exercise for you to work it out. Not on an exam again, but, after class, start with the polar coordinate transformation and work out what the Jacobian is. It's a nice exercise, a nice simple exercise. We just did it. But now let's consider this. Let's graph this domain here, see what we're dealing with. X squared plus y squared equal to 4, you know what that is. That's a circle of radius 2 centered at the origin. Very nice. X equals 0 is the y-axis. Y equals x is that. And we want the first quadrant. So what does this mean? I believe that we are referring to this region right here. Everybody comfortable with that? How are we doing? All right. Let's set up the integral just in terms of x and y, just to see what is happening here. Let's set up the integral in terms of x and y. So, obviously the question arises, let's do it here. The question arises, Do we want to set it up dx dy or dy dx? That's up to you. You tell me, what do you want to do? We have options. Whatever you want to do, dx dy or dy dx? Well, let's set it up both ways. Yishan is saying dx dy dx. Let's do that. Then we'll set it up dx dy just to see the difference for fun. How does y vary? This is the region. Y goes from y goes from the straight line, y equals x, to the circle, y equals square root of 4 minus x squared. Very nice. Very nice, Ahmad. And once you've described y, you would now project onto the x-axis. And the shadow cast by this object is going to be dependent on this point of intersection. Where does y equal to x intersect the circle? If y is equal to x, then this is x squared plus x squared. So this is 2x squared equal to 4. X squared is equal to 2. X is plus or minus root 2. But of course, you know that is the positive. So once y has been described, you project onto the x-axis, and you get 0 to root 2. There it is. It's not a difficult integral. Everything works out fairly well, and you're certainly welcome to evaluate it. But this is, well, I mean, let's evaluate just for fun. If we plug in, well, I mean, take the antiderivative. Let me not skip a step here. Antiderivative with respect to y. And you know, we're going to redo this question. We're going to redo the question in another fashion, and we're going to compare our answers just to see. If we integrate, can we do that in our heads? This is minus 2/3, 4 minus x squared to the 3/2. Minus 1/2, 4x minus 1/3 x cubed, minus 2/3 x cubed. I should have. Yeah. There's too many things there. If I expand this, I get a 1/2 x squared plus 1/2 x squared, that is x squared, minus 2x squared, so you get a just 1x squared. So minus 1/2 4x, that's this part. And then 1/2 x squared plus 1/2 x squared, that's x squared. Minus 2x squared, that is minus x squared, so minus 1/3 x cubed. All right. And what is this? This is minus 2/3. And this is going to be 2 to the 3 over 2. And this is minus 2 root 2 minus 2 root 2 over 3. When you plug in 0, this is 248. So that's 16 over 3. All right, whatever. Does that simplify somewhat? This is 2 root 2, so that's 4 root 2 minus 2, that's 6 root 2. So that's going to be a 2 root 2 minus 2 root 2, that's minus 4. This is apparently the answer. Is that correct? Does anybody have that? Minus 4 root 2 plus 16 over 3? We'll see. We'll see, because we're going to redo this question. Using polar coordinates. Thank you, Nemo. We're going to switch to polar coordinates. See what happens. The answers should agree. How do we first of all, let's look at our integrand. You know the polar coordinates. X is our cos, y is our sine. So your integrand 2x minus y becomes 2r cos minus r sine, right? 2x minus y. Jacobian r dr d theta. Now the question is, how do we describe this region here in terms of r and theta? You know r is measured from the origin going out. So r goes from the origin to the circle. The circle, which has equation x squared plus y squared equals 4. If x is r cos and y is r sine, you get r squared cos squared plus r squared sine squared, which is r squared equals 4 or r equals 2. Quinn is asking if we always integrate in terms of r first, never theta first. It's customary to integrate with respect to r first, and I'll tell you why. You usually have r in terms of theta and almost never the other way around. Right? And think about how we were graphing. We were graphing r equals a function of theta, never theta equals a function of r. So that's why you almost always integrate with respect to r first. So I think we've established that r goes from the origin to the circle. Circle has equation r equals to 2. So r goes from 0 to 2. And then theta goes from here to there. Right? You know how theta is measured. Theta goes from here to there. So Yining is saying we always consider that r is positive. I always consider that r is positive. I know some of you will want to relax that, but remember, it's absolute value of the Jacobian. So if you want to relax, you're going to be careful and throw in an absolute value here. And Kun is absolutely right. Y equals x corresponds to theta being pi over 4. If you didn't see that, let's look at it. Y equals x, so r sine theta equals r cos theta. The r's cancel out. When is sine equal to cos? When theta is pi over 4. Right? G is asking if we can explain how to get r equals 2. We had convinced ourselves that r goes from the origin to the circle, right? That's how r is measured, from the origin outwards. So from the origin, and you stop once you hit the circle. Circle has equation x squared plus y squared equal to 4. X is r cos, so x squared plus y squared equal to 4. This is r squared cos squared plus r squared sine squared. And if you factor out an r squared, you get cos squared plus sine squared, which you know to be 1. So r squared is 4. So r is plus or minus 2, but for simplicity, we're going to take r equal to 2. The circle has equation r equals 2. It's all points that are 2 away from the origin. And as Kun suggested, theta varies from pi over 4 to pi over 2. All right, let's see what happens. So we have 2r squared, which is 2 over 3r cubed, minus r squared, which is 1/3 r cubed, between 0 and 2. So 2, 4, 8, 16 over 3. Minus 8 over 3. And that is 16 over 3 sine plus 8 over 3 cos. From pi over 4 to pi over 2. Sine of pi over 2 is 1. Cosine of pi over 2 is 0. Subtract, plugging in, 1 over root 2 minus 8 over 3 root 2. So that is 24 over, wait, is it? 24 over 3 root 2. So 24 over 3 is 8 over root 2, or if you multiply by root 2 over root 2, this is minus 4 root 2, which is exactly what we have. There it is. There it is. Is it possible that integration with respect to x and y is not possible? So we are forced to use r and theta. The not possible is probably not true, but so hard. Well, actually, yes. I do know of an example where it's impossible to integrate with respect to x and y, and you are forced to use r and theta. Absolutely. Yes. So the answer is yes. Cecilia is asking, do we need to use the 1/2 f squared formula here? I mean, we're not using that, right? But you bring up a very interesting question. And let's address it now. Yining is asking if we're always using dr d theta. Well, I mean, I'm not sure what that means. This is a change of variables. It's only here to help you. Only here to help you. So, you use it if you want it to help you. If you don't use it. It's up to you. It's just a tool to help you here. But let's go back to Cecile's question. Recall. Consider this, right? When we developed the whole area in polar coordinates, we saw that the area was the integral from a to b, say, of 1/2 f squared d theta. Let's set this up. Let's derive this formula in a different way. You know that the area as a double integral is what? To get the area, you integrate what? To get the area of a region. You know what you integrate? You integrate 1, right? If you're on a region, you're going to integrate 1, you're going to get a volume, right? Imagine a function that is 1 above this. It hovers. You get a volume, but numerically it's the same as the area. Thank you. So this is the area of the domain D. Let's switch to polar. Switch to polar coordinates. Right? This is our domain D. This is what we want to integrate. So we're going to switch to polar to help us describe this region. You're switching to polar, you know that you want to throw in the Jacobian. So it's 1 times r dr d theta. How does r vary? R goes from the origin to your function. So r goes from 0 to your function. What about theta? Theta goes from A to B. Let's integrate. You can integrate with respect to r, and what do you get? You get 1/2 r squared. Or 1/2 f squared d theta, exactly your area formula that you knew. The area formula we had derived originally. Isn't that nice? Thereby reinforcing the need for the Jacobian there. All right, take a moment and graph the region we're integrating over. What are these things? You know what they are. These are two circles centered at the origin. One of radius A, the other one of radius B, where A is the smaller of the two. So one small circle and one larger one. And we are integrating over the region between the two. Let's think about setting this up in terms of x and y? Can we set this up in terms of x and y? Let's try setting it up dy dx, just for fun. How does y vary? You see what's happening, right? How does y vary? Y goes from here to there. For a while, until you hit this point. And now it changes. Now it goes from here to there. But also here to there. For a while, right, until you hit this point. And you know, and then it goes from here to there. So you understand what's really happening, right? If you want to integrate dy dx, you're going to have to split it up into 4 regions. This region, that region, that region, and this one right here. 4 pieces. You're going to have to split up the integral into 4 pieces. And then look at the integrand itself. How do you integrate that? Integration dy, you're going to have to do some trig substitution for each of the 4 different integrals. And then you haven't even integrated with respect to x yet. So I mean, it's going to be hell. It's going to be a tremendous amount of work. Convince yourselves. And perhaps you're thinking, well, I'm gonna integrate with respect to x instead, but it's the same issue. How does x vary? X goes from here to there for a while until you hit this point, and then it goes from here to there, and then here to there. So you're still splitting it up into 4 pieces. So that's no good either. Yining is asking, can we just split it into 4 pieces? Into 2 pieces, big circle and small circle. So you mean integrate over the large one and subtract the integration over the small one? Fine. Good point. Good point. You could do that. You could do that. So that would cut your work down by half. Very nice. But you'd still have to split it up into 2 pieces. And then there's going to be some trig substitution. Still a lot of work. Instead, we're going to switch to polar. We're going to switch to polar. Because how do you describe this in polar coordinates? How does r vary? R, as you know, is measured from the origin moving out. Your region starts when you hit the small circle and goes until you hit the large one. And that's always the case. The small circle has equation x squared plus y squared equals a squared, and we've worked out x squared plus y squared in polar coordinates enough times that you know that this is r squared. So the small circle has equation r equals a. The large circle has equation r equals b. So r goes from a to b. Very nice, simple description. What about theta? Imagine that you have this line segment. If you spin it around 360 degrees, you have described every point in this region. So r goes from a to b. R goes from a to b. Theta goes from 0 to 2 pi. This is a very nice, simple description in the r theta plane. Now look at your integrand. X squared plus y squared in the denominator. You know in polar coordinates, this is very nice. X squared plus y squared in polar coordinates is r squared. Y is r sine theta. Jacobian dr d theta. This is r squared. These cancel out, and you get r sine theta. R sine squared, rather. A trivial integral. So instead of having to break it up into 4 pieces and using some crazy trig substitution for just the first integrals, maybe for the second as well, who knows? You end up, by making a switch to polar coordinates, you end up with a very simple, straightforward integral. Integrated with respect to r. Sine squared is 1/2 1 minus cos 2 theta. So this is 1/4 b squared minus a squared. Antiderivative of this, theta minus 1/2 sine 2 theta. Between 0 and pi, 2 pi rather. And that is pi over 2 b squared minus a squared. So Sid is asking, if we integrate until 4 pi, does it give twice the area? Well, first of all, it's not an area question, right? But it's a volume. You have this function hovering above that region. But yes, it's going to give twice the volume. Absolutely. How are we doing? So you see the power of the polar coordinates, right? This would have been, and you know, I mean, it's an important exercise to try. This would have been hell to integrate with respect to x or y. Yishen is asking if we can integrate from 0 to pi over 2 and multiply by 4, because you have some obvious symmetry, right? This region is the same as that region, which is the same as that one, which is the same as that one, but you have to be careful. You have to be careful because you have this function hovering above. You have this function hovering above. And not only do you want the region of integration to be the same, but you also want the function to be the same. And are they necessarily? That's the question you have to ask. And let's address that. For every point xy here, you have a corresponding point, negative xy, on this side. And the height of your function is the same at both of these points. And for every point xy here, you have a corresponding point, x negative y. And the function at xy is the same as the function at x negative y. So you're fine. You're fine, and the answer is yes. You could integrate from 0 to pi over 2 here and multiply by 4. But you need to justify that, not only to the marker, but to yourself as well. It's not immediately clear that you can do that. You need symmetry of the region of integration, but also of the original function. So Yishen is following that up with the question, is the condition that it's symmetrical along x and y? That will do it, yes. And Ranji is asking, we chose dr d theta because r is a function of theta. Absolutely. Even though here r, there is no theta there, we're going to, I'm sure, come up with an example where that occurs immediately. Indeed, I believe the next question will be just that. All right. Take a moment, graph this. What region are we talking about? Are you graphing it? We've seen this before. If we complete the square by adding 1 to both sides, This over there was a circle of radius 2, centered at the origin. And this is a circle of radius 1, centered at 1, 0. So it's the region between these two. In the first quadrant. Excellent. Everybody with us? Now again, imagine setting this up in terms of x and y. It's not impossible. Why don't we set it up? X dy dx. How does y vary? How does y vary? Y goes from here to there. Y goes from the small circle to the large circle. Small circle has equation square root of 2x minus x squared. Large circle has equation square root of 4 minus x squared. And then you would project onto the x-axis. You see what this projects onto. The interval 0 to 2. Integration with respect to y is easy enough. There's no y anywhere, so we're good to go. And we would get x times this minus x times that. X times this is easy to integrate with respect to x. A simple u substitution does the trick. But x times that, we're in trouble. Not a great deal of trouble, but you have to complete the square, make a trig substitution. There's a bit of work there. There's enough work that we're going to ask the question, what if we switched to polar? Would it make the whole thing simpler? It's a valid question. Again, polar coordinates only there to help you. If you don't want to use them, don't. You can integrate by making a trig sub at some point, and it's fine. Switching to polar, probably going to be easier here. Let's see. The integrand, x, is r cos Jacobian dr d theta. How does r vary? R goes from oh, video's off. I didn't touch anything. Is the sound still on? Samuel and Prün? Is everything back? Let's give them a moment. Hopefully works now very well. Hopefully there won't be a stop in the video recording. Let's hope for the best. Right, so R is going from the small circle to the large one, but we're going to have to be careful here, because once you've described how R varies, we're going to ask the question, what about theta? What about theta? And theta, for the large circle, right? I mean, the large circle has equation R equals to 2. So this large circle, this part of the large circle is realized for theta going from 0 to pi over 2. Right? It's just a quarter of the circle and you're good to go. However, the smaller circle in polar coordinates has equation x squared plus y squared is r squared, and x is r cos. So this smaller circle here has equation r equals 2 cosine. You might not remember, but let's take a moment to graph that. R equals 2 cos. Right? How does that work? R starts at 2 and goes all the way down to 0 at pi over 2. So you've realized half the circle in 0 to pi over 2. So this half is realized in 0 to pi over 2, whereas this 1/4 is realized in 0 to pi over 4. So you want to be careful. You want to be careful. So we cannot set it up as a single integral here. We have to split it up into 2 pieces because the values of theta vary depending on the large versus the small circle. So what are we going to do? We're going to say, we're going to do the large circle from 0. So r goes from 0 to 2. So first of all, it's r squared cos theta, dr d theta, where r goes from 0 to 2. Theta goes from 0 to pi over 4. Not pi over 4, but pi over 2, right? We're going to take the quarter circle, and then we're going to subtract the stuff in the smaller one, where here r goes from 0 to the small circle. And the small circle has equation right? So here r goes from 0 to 2 cos theta. And theta goes from 0 to... Oh no, so we were fine. What was I doing? I don't know what I was doing. Somehow I thought they were going to be different. They're not. They're not different. Sorry about the confusion there. Sorry about the confusion. So there was no need to break them up. Yeah, there was no need to break them up. I'm not sure what I was thinking. Not sure what I was thinking, but yeah, because this is pi over 2, and this is pi over 2 as well. So everything is pi over 2. In other words, there was no need to break it up. You were going from the small circle to the large circle. So small circle to the large circle, and theta was going from 0 to pi over 2. It is half, but this half is realized in 0 to pi over 2 only. Right? So maybe I wanted to bring your attention to the fact that it wasn't realized in 0 to pi, but rather 0 to pi over 2. There are several questions here. It's all my fault. So originally, Quinn was saying, can we take theta from 0 to pi over 2 of the large circle and 0 r from 0 to 2 and minus half of the area? Well, I mean, you want to be careful, right? It's not half of the area because you have an integrand there as well. But so Yining is suggesting 0 to pi, but no, it's 0 to pi over 2 for both. Ranji, cosine of pi is -1, which makes r -2, isn't it? Yes, but we didn't go all the way to pi because that would have been the bottom half. We didn't need to worry about that. We just wanted the top half. I was trying to find the angle where r is 0 to 2. How to find that? I'm not sure what you mean, Ishen. But, I mean, look, if you split it up, you get this. And since these two things are the same, you can just subtract those. And you know how to subtract two integrals, right? 0 to 2 minus 0 to that, you just get 2 to that, which is what we would have gotten if we hadn't split it up anyway. So, I mean, we're good. We're good. It's all good. It's all good. Sorry about the confusion there. I was worried you had to split it up. Originally, you did not. All right. With that aside, integration is fairly straightforward here. This is 1/3 r cubed from 2 cos to 2. Which is 8 over 3 minus 8 over 3 cos cubed, the whole thing times cosine d theta. And what is that? That's 8 over 3 cos minus 8 over 3 cosine to the 4. And while the cosine of the 4 is a bit, I mean, it's not tricky, I wouldn't say tricky, but you know what to do, right? You're going to rewrite this. So first of all, let's do this one. That's 8 over 3 sine from 0 to pi over 2. minus 8 over 3. Cosine of 4 is cosine squared, which is 1/2 1 plus cosine 2 theta. All squared, half angle, right? Sine of pi over 2 is 1. Sine of 0 is 0, so that's an 8 over 3. And then if you square that, you get a 1/4, which I'll take outside. And you get 1 plus 2 cos plus cos squared. So 8 over 3 minus 2 over 3 times that integral. And this cosine squared, I'll use the half angle identity again. So I get a 3 over 2, right? And he's going to 1/2 plus the 1, that's 3 over 2. 2 cos 2 theta. And then 1/2 cosine 4 theta. Let's finish that up. 3 over 2 theta. Sine of 2 theta. 1 over 8 sine of 4 theta between 0 and pi over 2. Sine of pi is 0, sine of 2 pi is 0, sine of 0 is 0. So these cancel out nicely, and we'll get an 8 over 3 minus pi over 2. I think. Anybody? Thank you. Let's do one more. Let's take a moment to graph this. What are we talking about? Let's start by graphing this business. Z equals square root of x squared plus y squared. We've seen this before. But let's recall how we graph in 3D, right? I mean, we graph in 2D. Take y to be 0. Graph this in the xz plane. If y is 0, z is the absolute value of x. And you know what that looks like. There's no hesitation there. It's just this V shape. And if x is 0 in the yz plane, again, z is absolute value of y. So it's just this V shape in the yz plane. And then we put everything together by looking at level curves. What happens if you slice? If z is c, you have X squared plus y squared is equal to c squared. So you put everything together with circles. You have this cone shape. So you have this cone shape along the z-axis. And then what is this? Well, this is x squared plus y squared bigger than or equal to 1. So you have a circle of radius 1 centered at the origin. And x and y are larger than that, so they live outside of that. But x squared plus y squared is less than or equal to 4. So x squared plus y squared equals 4 is a circle of radius 2. Centered at the origin. So again, we are restricting our attention to this region between the two circles, but underneath the cone. So what is the volume underneath the cone restricted to the region between those two circles? Let's set it up. We're looking for volume. We're looking for the volume underneath this function. So you know that the integrand is just going to be this, where you're restricted to the region R, let's call it R, between the two circles. First of all, without doing any work, you understand that if you want to integrate with respect to y or x, it doesn't matter. But how do you find the antiderivative here? If you're integrating with respect to y, you're going to treat x as a constant, and this calls for, how do you integrate with respect to y? Well, there is quite a lag there, but you know the answer to that. Thank you, Ben. Trig sub, namely a tangent substitution, which is quite a bit of work. Let's not go there. Moreover, we just did an example of that, and you understand that if you're integrating with respect to y, y is going to vary from the large circle to the large circle for a while, and then large circle to small circle and small to large, and all that to say that you're going to have to split it up into 4 regions. So not only a trig sub, but 4 trig subs, because you're splitting it up into 4 pieces. Way too much work. Way too much work. We're going to switch to polar. We're going to switch to polar and hope for the best. And the beauty in polar coordinates, x squared plus y squared is, we've done it many times, it's r squared. So this is the square root of r squared, Jacobian dr d theta. And we've understood how r varies, right? R goes from 1 to 2. And then you spin that around 360 degrees. That will describe every point in your region. So R goes from 1 to 2, theta goes from 0 to 2 pi, and you're done. Integration is trivial. There is no theta. So by Fubini's theorem, you could integrate it with respect to theta first. And you just get a 2 pi. This is r squared, whose antiderivative is 1/3 r cubed from 1 to 2. And this is 8 minus 1 is 7 over 3. 14 pi over 3. Well, how do we get the volume equation? You know that a double integral is really the volume underneath the function. And that's what we're looking for. We're looking for the volume below this function, but above this region. So it's the volume underneath the function above the xy plane. How are we doing? Questions here? Can we integrate by switching to d theta dr? You can, right? Because Fubini's theorem applies here as well. As long as the integral of the absolute value is finite, you can switch. And that's exactly what I did. So it's the volume of a cylinder with a spike cut out of the middle. Okay, I see what you're saying, right? I mean, you could have viewed this as a cylinder and then you're removing part of it. Absolutely. Absolutely. Yishen wants to confirm R doesn't really matter. I'm not sure what you mean here. R doesn't really matter. How so? What R? Negative R? Well, right, because you're thinking to yourself, the square root of R squared really should be absolute value of R, but you know the Jacobian should be absolute value of R again, right? So, look, I mean, I don't want to say I'll never I'll never work with a negative R. But let me say it anyways. I'm never going to work with a negative R. You should not work with a negative R either. I know some of you are going to want to, and I'll be fine with it as long as you remember that it's absolute value of the Jacobian. Because if you're working with negative R's and you don't have absolute value of a Jacobian, we're going to have an issue. So keep that in mind. Any other questions? How are we doing with everything? Practice this. We'll pick this up again tomorrow and discuss the triple integral. You guys have a good one. I'll see you tomorrow.